So we have discussed the equivalent circuit of BJT. We have defined different parameters. So you have base terminal, emitter terminal and collector terminal. And then you have the values of C pi, input resistance and capacitances. Then you have R mu and C mu. So in some cases you will find people write it small R mu. So this is the GMVB, the current source, and this is output resistance. And this RB, RC and RES are the external resistances that we have discussed at the end of the analysis of different parameters. So in many cases you can neglect this internal B dash, E dash and C dash. This part is the internal part of the transistor. However, these are the external parameters that in many cases you can neglect. However, you can keep them for better accuracy. But most of the time, these internal points are considered. This B dash, C dash and E dash. And this is the input voltage VBE. Okay. So all these parameters I have discussed, also have shown the analysis of the same. So it is important to know what parameter is what. Otherwise, while you are designing, things may become blurry. So this is the parameters. Let us see some of the typical parameters, the values that are associated with these parameters. Okay, so before that, let us see something which is, we know this IC and VC. This is the output characteristics, wherein for different gate voltage you are getting these different output characteristics of the BJT. Now if you see the circuit here, you have VCC, then you have RC and the emitter of the same is grounded. So this is emitter, base and collector, and emitter of the same, emitter of this circuit is grounded, and IC is flowing from collector, from the collector side to the emitter. Okay, now if you just do an KVL of this particular circuit, this is common emitter configuration. If you do an KVL of the same thing, so you have VCC, you will find a voltage drop in this. So VCC will be equal to IC into RC plus VCE, whatever is the voltage here. This is grounded, right? So you just take this path for the KVL analysis and you will find VCC equal to ICRC into VCE. Now this is a linear relationship. If you draw the same thing, you have VC and IC, right? So VC is your x-axis and IC is your y-axis. Now if you just plot the same thing in the output characteristics, you will find a straight line like this. How do you get the straight line? You just convert it to a form of x by a plus y by b equal to 1. Okay, so for that purpose, what you will do? Just divide everything by VCC. So you will find 1 equal to ICRC by VCC plus VCE by VCC. So this is your x, right? This is your x and this IC is your y. So x by a, your a is VCC. So it will cut the x-axis at VCC. Okay. And this is your y. So y by b. Your b is basically VCC divided by RC. So if you write it in this way, just bring the RC in the bottom. So it is y by b. Your b is VCC by RC. So you have VCC by RC here. Draw the line. So this is what the straight line is in your output characteristics, and this line is known as load line. Probably you have done it previously as well. But if you see the load line, you will find your bias points. Now at a bias point, say you are taking this IB into the consideration. You want to bias your circuit at IB3. So you will find that, okay, this is my bias point, and this bias point will give you a biasing voltage and biasing current. And I already have said this biasing current is very important in GM, in beta. In most of the parameters you have seen that IC is a function. So this is very important. Now let us look at different these parameters. Why I have shown is because the first term I have mentioned here biasing. So you have IC value. That's why I have shown this is how you choose your biasing. Here say this ICV value is 1 milliampere. These are typical values. Okay, it's just to give you an understanding about the numbers. What are the values? What is the magnitude of those values? So your biasing current here is 1 milliampere. Your VCB, that means what is VCB? If you draw the transistor again, C, E, and this is B, right? So your VCB is the reverse bias voltage. So reverse bias voltage is 3 volt. Your VCE means the voltage here. It is 5 volt. The typical capacitance values are CJ0. What is CJ0? CJ0 is the no bias capacitance. That is when biasing is not there. What is the capacitance of emitter junction? I already have given you the expression for this CJE, that is junction capacitance of emitter here. Junction capacitance here. Okay, which is typically 10 femtofarad. Femto means 10 to the power minus 15. The built-in potential at emitter is 0.9 volt. And this value, this is N value. In the expression, you have an N value while you are calculating the capacitance. This N value is 1 by 2. However, for collector, the C mu O is 10 femtofarad. The built-in potential is 0.5 volt and the N value is 1 by 3. Now this value depends on mostly like the way it is fabricated. If it is a step junction, it is half. If it is a linearly graded or say exponentially graded, the values will differ. So based on that, you can choose whether it is 1 by 2 or 1 by 3. Generally, the emitter junction is step graded and the collector junction is either linearly or exponentially, or it may be other way around. It depends on the fabrication. So based on that, you can select the N value. However, in here I am giving you untypical values. Okay, then you have substrate. So in the substrate, CSO0 is 20 femtofarad. The built-in potential is 0.65 volt and you have N equal to 1 by 3. So here these are the typical values. Okay, so more or less all these no bias capacitances are in femtofarad range. Okay, this is what we should understand. Then you have beta 0 value, which is typically 100. Tau b is the base transit time. The time taken by a carrier to go from collector to emitter is around 10 picosecond. So the typical value is in picosecond. Then you have early voltage is equal to 20 volts. Now, what does early voltage show? Early voltage shows you the output resistance, right? We will see output resistance. If you remember, I have already explained, if these are your characteristics and if you just extend them, you'll find it is touching VCE axis at the early voltage, and this voltage can be used for calculating the output resistance. So higher the VA value, better is your device, because your out resistance ideally should be infinite. So you want a very high value over there. Then the resistances that I have shown, VBB dash, RE dash and RC, the typical values is 300 ohms, RE value is 5 ohm and RC value is 50 ohm. Now you can see clearly RE value, that means the emitter resistance is lower than the collector, which is obvious because emitter is highly doped, N plus. Your emitter is generally N plus, if you remember the figure. So if it is NPN, this is your emitter, this is your base, this is your collector. So this part is highly doped. n plus, so that is reflecting here. The emitter resistance should be lower, and it almost 10 times lower, so you can understand that doping is quite high. And then you have R mu. What is the R mu? You remember? You check here, this is your R mu. So this R mu value we already have derived. This R mu value is 10 beta 0 R0. So it depends on beta 0, that is the gain, and R0, the output resistance as well. Okay, so this is your circuit, and these are the different parameters given. So this slide is very important. See, from these values we will calculate or evaluate some other values. So you will get a lot of questions from these two slides. So it is important that you pay attention to these slides, and also you at least derive those equations that I have already derived for you in your home, so that you get the equations in your mind. So it should be very clear, otherwise you'll see there are a lot of troubles, okay, while calculating. So these are the typical values. Now from these values we will evaluate few other values. Okay, see, so the coming few slides is very important because I have summarized all the equations over here. It will be easier for you to go through, and also in different competitive exams you will find these are very important. So you will get a lot of questions from based on these equations from BJTs. Okay, so it is good advice. I'll recommend all of you to at least once derive those equations in your home. So take it as an homework and just do it by yourself. Then your conception will be even better. So memorizing something will put load in your memory, right? Rather, if you do it by yourself, you don't need to memorize. It will be there in your memory because you have done it by yourself. Okay, so these are the values that are given. I have kept all the values over here. The fonts are little small, but I think it's still visible. Okay, so now you evaluate the value of CJE. What is CJE? The base emitter junction capacitance. The junction capacitance, I said, it's an empirical formula which is twice the value of CJEO. So you have CJEO given here 10 femtofarad. Put 10 femtofarad twice into 10 femtofarad, you have 20 femtofarad. Then you have C mu. What is C mu? If you remember, this is your base, this is your collector, this is your emitter. You have R mu and a C mu in parallel, right? So you have C mu value is C mu 0 divided by 1 plus V CV divided by phi 0 C. Okay, so in this case all these values are already given. C mu 0 is given, VCB is given 3 volts, and phi 0 C is given 0.5, N is also given 1 by 3. So you have 5.6 femtofarads. Then you have similarly CS values. Now if you look, all these capacitances are also a function of frequency, because ultimately the impedance Z equal to 1 by J omega C, right? So the impedance is a function of frequency as well. This is frequency, right? So for different frequency you will find these values are different. However, we also have this is frequency dependent. However, we also are calculating these values based on the values given. Okay, but they may vary with, the effect of them, not this value, not the value of C. Value of C is there, but the effect of these values will vary with frequency, because ultimately the impedance is what you are looking for in the circuit, right? So the effect of this is frequency dependent. So frequency will play a big role. Even if you have, for example, say C very low, so your impedance is high, you will find at high frequency, if your omega becomes very high, again Z will come down for a given C. So these frequency effects are also very important, that we will see later. Then you have GM value. So the GM value is QIC by KT. So the IC value, all these values are given. T is, I think, 300 Kelvin you can take. If it is not mentioned, you can take T to be 300 Kelvin anywhere, unless and otherwise specified. If it is specified, that is different. Otherwise, you take T equal to 300 Kelvin. So you will find this value is 38 milliampere per volt. So somebody also may write this as millisiemens. That is not a problem, but the convention is you write like this, milliampere by volt. So it's like volt ampere current by voltage ratio. Okay, so that it gives, it's a bit easier to interpret. Okay, then you have CB value. What is CB? CB is a component again in your input capacitance C pi. This is diffusion capacitance, which is GM tau B. So you have GM value already calculated from here, and then you have tau B given here, which is coming to be around 0.38 picofarad. Okay, then you can calculate the input capacitance C pi. What is C pi? You can see in the circuit itself. This is your C pi. So if you look at from this side, this is your C pi. So your C pi value is now summation of CBE, which is also known as C pi dash by CJE. So 0.38 picofarad is CJE. CJE is 0.2. So it is pico. I'm keeping both of them pico. So if it is 20 femto, and if I convert it to pico, it will come at 0.02 picofarad, and you just calculated CBE to be 0.38 picofarad. So you have 0.38 plus 0.02 as 0.4 picofarad. Now if you see, the value of diffusion capacitance is higher, but which one is dominating? If you think from Z in perspective, that is the impedance perspective, that is 1 by j omega c. Again, 1 by j omega c. So C high means your Z is low. From that perspective, your junction capacitance is dominant from impedance perspective. However, from value wise, this is higher. Your diffusion capacitance is higher. Okay. So this is what we should keep in our mind. Then we have R pi value. What is R pi value? Input impedance. Sorry, input resistance, not impedance. Input resistance, R pi. With C pi, you have R pi. Again, we will go there and we'll see. This is your input resistance. This is your input capacitance. So input capacitance we already have calculated. Input resistance we are now going to calculate. Let's see here. It is beta 0 by GM, right? So beta 0 given, GM you have calculated, so it is 26 kilo ohm. Now see, this is a function of GM, and if you see here, GM is a function of IC, right? GM is a function of IC. So biasing current is very important. It is also going to influence your input, resistance. Okay. So it is 26 kilo ohm. Now, what should be your input resistance? What do you expect? Your input resistance should be high, because if it is not high, let's go back to the circuit. If it is not high, everything will come and go from here. You will not get anything in the circuit. Most of the current will pass through. It will act as a short circuit. So you want this input to be high. So this is your input resistance. Then you have output resistance. Output resistance is VA by IC. We already have calculated. See, here also IC is a factor. So both input and output resistance will depend on your biasing current. That is this one. where are you biasing. Okay, so it is important, your biasing current is important. Now VA by IC, now the value of VA is given is 20, so ideally you want a very high VA. If the VA is very high, your output resistance will be higher, and output resistance you want to be higher because there is an current source. You want the current source, you want the resistance parallel to this current source to be very high. Okay, so this one R0 you want to be higher, so you expect a higher VA value. So you can see here here you can see the values are given. VA is 20 volt, it is given. See from here where it is given, VA is equal to 20 volt, and then you have IC value as 1 milliampere here. So you have 20 kilo ohm as an output resistance, and then you have R mu. But which one is R mu? R mu is this value, right? So the R mu value will be 10 beta 0 R0. So you have beta 0, you have R0, which is going to be 20 mega ohm. So it's a very big, very high resistance. In that case, I think you can neglect R mu. Okay, so these kind of calculations you have to perform while you are going for the design. So most of the time the approximations are very important. As an engineer, you should know which value to consider, which value not to consider. For example, the R mu value is very high, so in the circuit you can, okay, that is not important, so you can remove that R mu. Okay, and in some cases, if for example say if you take this one, if you calculate only CBE, that is okay, you are getting 0.38 picofarad, your CJE is compared to this is very low, so ultimately we'll see the R pi value, right? So 0.38 and 0.4, not very high. So maybe in that case you can, while you are doing your first calculation, just to give you an estimate, just to give somebody an estimate, just to give somebody an idea, just quickly you can do these calculations and can give an estimate. Okay, even in competitive examinations, sometimes some questions will come, and in that case, just to get, nowadays it's multiple choice, right? So if you can approximate your answer very well, you'll get the answer. So you don't need to do the entire thing. If you sit and take each and every value like 0.001 along with say a value like 10, then things become more complicated, because 0.001 is very, very less compared to 10. So physics wise, probably you have to consider everything, but circuit wise, when you are doing some engineering, you can neglect those values. This is up to you, how good approximation you can make, how quick calculation you can do. So these 2 slides that I have shown is very important from different examination perspective, competitive examinations perspective, from understanding perspective, to get some idea about typical values of the circuit parameters, which is also important. What is the value of CJE, C mu that you will get? At least you should know these are in femtofarad range. So this will give you an idea, typical values. These are okay. In special cases they may vary. In special cases you also may need to do something where the CJE is probably not femto. You want this to be pico. That is different case. But at least the typical values you will get from here. So this 2 slides is important.